Good day, everyone. Today we will be discussing different sensors and transducers. We will explore what they are, how they work, the different types used in engineering and technology, and why they are important in modern systems. Sensors and transducers play an essential role in converting physical quantities into useful signals. They enable automation, monitoring, and control in various fields such as electronics, robotics, medicine, and industrial applications. First, let us define what is a sensor. A sensor is a device that detects or measures a physical quantity such as temperature, pressure, or light and converts it into a readable signal. In short, it senses changes in the environment. Transducer, on the other hand, is a broader device that converts one form of energy into another. A sensor is actually a type of transducer, but not all transducers are sensors. Examples include microphones, which convert sound energy into electrical signals, and speakers, which do the reverse. What is the difference between sensors and transducers? Sensors focus on detection, while transducers encompass both detection and conversion. A sensor outputs information, a transducer outputs energy or signals. Think of it, sensor as the input detectors, while transducers are the energy converters. Sensors can be classified based on the type of input or physical quantity they detect. This classification helps us select the appropriate sensor for specific applications. The major categories include temperature sensors. It detects heat or cold and measure temperature changes. Motion sensors detect movement or displacement of objects or people. Pressure sensors sense force applied to a surface or fluid. Sound sensors detect acoustic vibrations or sound waves. Gas sensors identify the presence of concentration of gases in the environment. Magnetic field sensors detect magnetic poles, fields, and changes in magnetic strength. These classifications make it easier to understand how sensors operates and where they are best used. First classification of sensor that we're going to tackle is the temperature sensors. The first example is the thermistor. A thermistor is a resistor whose resistance changes significantly with temperature. Due to its sensitivity, it is widely used in signal thermometers, HVAC systems, and battery protection. An example is the thermocouple. Made from different metals joined together, a thermocouple generates voltage when heated. It is durable and suited for high temperature environments like furnaces and engines. One is the RTD, or the resistance temperature detector. RTDs use the predictable change in resistance of metal such as platinum to measure temperature accurately. They are used in laboratories, food processing, and precision industrial control. One is the infrared temperature sensor. This sensor measures temperature without physical contact by detecting infrared radiation emitted by objects. Common uses include medical thermometers, thermal cameras, and equipped monitoring. The next classification of sensor is the proximity sensor. The first example of proximity sensor is the IR sensor, or the infrared sensor. An IR sensor emits infrared light and measures reflection to detect objects nearby, frequently used in robot obstacle detection, touchless switches, and home appliances. The second example is the ultrasonic sensor. Uses ultrasonic sound waves to calculate the distance of an object. It is widely used in parking assist systems, water level monitoring, and robotics. The third example is the capacitive sensor. It detects changes in capacitance to sense both metal and non-metal objects, used in touchscreens, material detection, and proximity. The fourth example is the inductive sensor. Uses electromagnetic fields to detect metal objects, commonly found in automation lines, conveyor belts, and industrial machinery. The fifth example are the Hall effect sensor. Senses magnetic fields and magnetic pole changes. Application include motor speed detection, wheel rotation sensor, and smartphone screen locking.
Light sensors. Examples: LDR or light dependent resistor, photodiode, phototransistor, color sensor. Pressure sensors. Examples: piezoelectric sensors, strain gauge, barometric sensors. Humidity sensors. Examples: capacitive humidity sensor, resistive humidity sensor, hygrometers. Gas and chemical sensors. Examples: MQ series sensors, pH sensor, oxygen sensor.
Motion and vibration sensors. First example is the accelerometer. An accelerometer is a device that measures acceleration, which is the rate of change of velocity. It works by detecting the force caused by gravity, vibration, or motion, often using piezoelectric crystals that generate an electric charge proportional to the force exerted on them. So next example is gyroscope. So a gyroscope sensors or angular velocity sensors measures an object's rotational motion or angular velocity or the rate of rotation in degrees per second. It works by detecting the Coriolis force or through the principle of angular momentum to sense changes in orientation along axes like roll, pitch, and yaw. So next is the PAR sensor. A PAR sensor or the passive infrared sensor is an electronic sensor that detects movement by sensing changes in infrared radiation emitted by warm objects like humans and animals. And the last example is the vibration sensor. So a vibration sensors are transducers that detect mechanical vibrations and convert them into measurable electrical signals. They are primarily used to quantify three fundamental physical quantities associated with vibration. So next is sound and acoustic sensors. So the first example is microphone. A microphone sensors are essential devices that allow us to capture sound and convert it into electrical signals, playing a crucial role in modern technology. So the next example is the ultrasonic transducer. So an ultrasonic transducer and ultrasonic sensors are devices that generate or sense ultrasound energy. They can be divided into three broad categories: the transmitters, receivers, and the transceivers. So the last example for the sound and acoustic sensors is the hydrophone. So just a microphone collects sound in the air, a hydrophone detects acoustic signals underwater. Most hydrophones are based on a special property of certain ceramics that produces a small electrical current when subjected to changes in underwater pressure. So next example is the magnetic sensor. A magnetic sensors are devices that detect and measure magnetic fields around permanent magnets, current conductors, and electrical devices. As the world becomes increasingly electrified, demand for improved positional and current sensing has grown in turn. So we have three examples for the magnetic sensor. The first one is the half-effect sensor. A half-effect sensor is a magnetic sensor that detects the presence and strength of a magnetic field and outputs a corresponding electrical signal. It works by using the Hall effect where a voltage is produced across an current-carrying conductor when it is placed in a magnetic field, deflecting charge carriers. So the second example is the flux gauge sensor. A flux gauge sensor are typically ring cores of a highly magnetically permeable alloy around which are wrapped two coil windings, the drive winding and the sense winding. Some sensor will also have a third feedback winding if the sensor is to operate in closed loop. So the last example is the magnetoresistive sensor. In simplified form, a magnetoresistive sensor functions as follows. An object with its own magnetic field approaches the sensor. As the result, the electrical resistance changes. This makes it possible to detect at what angle the external magnetic field and thus the object in position in relation to the sensor. So we have three examples for the optical sensor. The first one is the encoder sensor. An optical encoder sensor is a type of motion sensing device that uses light shown through a coded disk to track the movement of a shaft. The encoder provides feedback based on the interruption of light. The graphic below outlines the basic construction of an optical incremental rotary encoder. So the next example is the fiber optic sensor. So a Fiber optic sensors are defined as devices that utilize optical fibers to measure a variety of stimuli, including mechanical, thermal, electromagnetic, radiation, chemical, and flow characteristics. So the last example for the optical sensors is the photoelectric. So a photoelectric sensor is a type of switch that is turned off in and on by the presence of absence of received light. The inherent advantages of such a non-contact switch have resulted in widespread application throughout the industrial world.
So, what is a biosensor? A biosensor is an analytical device used for the detection of the chemical substance that combines a biological components with a sociochemical detector. So, our example for this is the glucose sensor. So, a glucose sensor is a continuous glucose monitors or device that are essential tools for managing diabetes by providing real-time blood sugar levels without the need for the frequent finger pricks. It's a small device used for monitoring your blood sugar. Next is the heart rate sensor. Heart rate sensors are devices that measures your heart rate, commonly used with fitness tracking, health monitoring, and various DIY projects. So the example for this, the heart rate sensors are our smartwatch, which is it has the tools or the device can monitor your heart rate. So next is a pulse oximeter. So what is a pulse oximeter? A pulse oximeter is a non-invasive device that measures the oxygen saturation level in your blood, helping helping monitors helping monitor respiratory health and detect potential issues. So all of this, the biosensors is commonly used from the medical fields. So commonly you can see these tools in the medical field, such as nurses and doctors. So our next topic is force and load sensors. So what is force and load sensors? Force and load sensors are essential devices used to measure mechanical forces such as tension, compression, and shear, and they play a critical role in our various industrial applications. So our example for this is a load cell. So what is a load cell? A load cell is a transducer that converts force into a measurable electrical output, widely used in various applications for accurate weight measurements. And next is force sensitive resistor, or the FSR. A force-sensitive resistor is a type of sensor that detects physical pressure, squeezing, or weight by changing its resistance value in response to applied force. So example for this is the hydraulic press. Next is the piezoelectric sensors. So what is a piezoelectric sensors? A piezoelectric sensors is a device that converts mechanical energy into into electrical energy using the piezoelectric effect, allowing it to measure changes in pressure, acceleration, temperature, strain, and force. Next is level sensors. So what is level sensors? Level sensors are devices used to detect and measure the level of liquids or bulk materials in containers such as tanks and silos, employing various technologies for accurate monitoring. So example for this is the float sensor. So a float sensor is a device used to detect a level of liquid in a tank or a container. It operates using a buoyant object known as a float, which moves with the changes liquid level. As the float rises or falls, it it activates a switch or sends an electrical signals to control the system. So next is the capacitive level sensors. So a capacitive level sensors are a vital part for modern industrial systems and automation. they they are widely used by for measuring they are widely used for measuring the level of liquids, solids, and other powder and in various applications. These sensors function based on the principles of the capacitance, a property that enables them to detect the presence or the absence of the material without direct contact. Next is the ultrasonic level sensors. So, the ultrasonic level sensors are devices that measures the level of liquids or solids by emitting the electrical sonic pulse.
So here is another sensor and it is called the flow sensor. So what is a flow sensor, do we ask? A flow sensor, or often called as the flow meter, is a device that measures the rate up to which a fluid or gas moves through a pipe or a duct. So it converts the fluid into a readable output signal, which can be in terms of volume flow rate or mass flow rate. So here we have an examples of flow sensors. First, we have the turbine flow sensor. So the turbine flow sensor is a volumetric flow meter that uses the fluid's kinetic energy into and to measure its velocity. And another example we have is the ultrasonic flow sensor. So the ultrasonic flow sensors are non-intrusive devices that measures fluid velocity using sound waves. And the final example of flow sensors, we have the thermal flow sensor. So the thermal flow sensors, specifically thermal mass flow meters, directly measure the mass flow rate of gases and sometimes liquids based on heat transfer. And here is another example of a sensor. It is called position and displacement sensors. So what is a position and displacement sensor? So a position sensor is an electrical device that measures the position or travel of an object. The position can be linear, straight line movement, or angular, rotational movement. And a displacement sensor is essentially the same, as it measures the change in position relative to a reference point. These sensors convert the mechanical movement into a proportional electrical signal. For example, is voltage, current, or digital pulse. So here we have the examples of positions and displacement sensors. The first example, we have the potentiometer or POT. A potentiometer is a simple, cost-effective device that measures positioning by converting mechanical movement into a change in electrical resistance, which is then read as a proportional voltage. And another example we have is the LVDT, or the linear variable differential transformer. The LVDT is a highly accurate non-contact sensor for measuring linear displacement. And the last example we have is the rotary encoder. So a rotary encoder is an electromechanical device that converts angular position or motion of a shaft or axle into a analog or digital code. So why do sensors matter? Sensors and transducers allow machines to understand the physical world. Sensors matter because they are the bridge between the physical world and the digital world. They act as the eyes and ears of modern technology, collecting data about physical properties like temperature, pressure, motion, and light, and converting it into a usable electrical signal. So without sensors, systems would be blind and unable to react to their environment, making automation, smart technologies, safety, and data-driven decision-making impossible. And in conclusion,
In summary, sensors and transducers are the foundation of the modern engineering systems. They are often used interchangeably in general contexts, but in engineering, they have distinct, related roles. Both devices are essential for converting a physical event into a measurable signal, which is the foundation of all modern monitoring and controlling systems. Here are the image sources that we used for our report. Thank you for listening, and once again, I am James Lester Osabino, and we are from the Biliran Province State University. Thank you.